So I think I would like to start by introducing or reviewing the concept of a prop, so we're all on the same page. We have here the symmetric group, and I chose to present it with a certain number of generators. You can think of those as transpositions, and those transpositions satisfy the relations that we see on the right. Now, we think of a group action in an algebraic context as a structure preserving map from the group ring into the automorphism complex of M, say a module over the Z. And the groupness we could be captured if we didn't know what a group was. We could imagine arriving to this notion as Galois and others did through understanding the composition structure that this automorphism has. So we're gonna describe what props and operads are in a similar manner. We're not gonna define what a prop is, but we're gonna describe its structure through an example. A canonical example like the automorphisms. So the propness for us will be encoded in the compositional structure of this gadget here. So we're going to have for every pair of non-negative integers, the complex of linear maps between the tensor product of M with itself a bunch of times to the tensor product of M tensor with itself a bunch of times. So the compositional structure is what we're trying to abstract here, but we can also see that there's natural symmetric group actions. We act in the domain with sigma M, and we act on the target with sigma N. So that is the complete structure that we are going to be considering: multiple inputs and multiple outputs. Now, the notion of a prop action, or more commonly known as bialgebra over a prop, is a structure preserving map from the prop into this endomorphism prop for some M. We'll say that M is the one that carries the P bialgebra structure if such a morphism exists, or such a morphism is chosen. Now, the notion of an operad could be obtained from this notion of a prop by considering either M or N to be fixed and equal to 1. So we look at our example out here, the endomorphism. Just want to make sure, could you see my my cursor?
Yes. Great.
So if we look at the structure that we will get, if we were to fix, say, N to be equal to 1, then we'll have maps with multiple inputs to a single output. That will be an example of an operad. The compositional structure and the induced symmetric action, or the restriction of the symmetric action, is what we will be considering. And on the other hand, if we set M equals to 1, then that will be another example: one input into multiple outputs. So the point of view that we like to take here is maybe less common. I would prefer the single input to multiple outputs point of view. So I will be thinking co-algebraically instead of algebraically in the rest of the talk. So now, when we think of a presentation of a group, we had a certain number of generators, and those were just symbols. And the way that they are composed freely is through just concatenation. So the objects that play a similar role in the context of props are not just symbols, but there are directed label graphs. And we do not admit directed loops. Here, I haven't drawn the direction. I'm using the plane for that end. I would like to think of all the directions going from top to bottom. And the labeled part of this structure, the fact that all inputs are labeled with positive integers, all outputs at the bottom are labeled as well. And every time we have a vertex, we have orders, total orders on the incoming edges and on the outgoing edges. So here we can see in red choices for those labels. Now, similar to the fact that I did not consider explicitly the direction and I used the plane to describe the direction, I could use the plane to implicitly describe the labeling of the interior vertices. So we're always going to go from left to right. And if we need to flip it, well, we could go under, like we see over here, to put it in the canonical order that the plane imposes on us. Now, we said that these are playing the role of the symbols in the presentation of a group. Concatenation plays the role of composition in the group context. For us, we're going to have two types of operations. Grafting, so we're going to be able to insert one of these directed graphs into another, or we can, that's like a vertical composition, or we can have a horizontal composition given by disjoint union of two such graphs. And the last part of the structure of a prop given by the symmetric action, which in this case is given by relabeling inputs for us here at the top, or relabeling outputs here at the bottom. Now, if we restrict to operads, and we're setting the number of inputs to be 1 and multiple numbers of outputs, what do we mean by a presentation? Well, in this algebraic context, we want to give a certain number of generators. In this case, I'm just giving one generator. On passing, I'm omitting the labelings in the output. That is a reference to the fact that it's freely generated by the appropriate symmetric action. And here on the right, we have one relation. Now, the prop, in this case, the operad, that is generated by this presentation is known as the associative operad. This is not going to be the focus of our talk. There's another operad that we're more interested in, that is the terminal operad. And that is the commutative operad. We have still 1 to 2 operation like we did before, and it's also co-associative, but we want it to be co-unital as well. So we introduce a generator that has 1 input and 0 outputs, and that satisfies this co-unitality relation. Now, the action of the symmetric group here will be trivial. So we're identifying as part of the list of relations that this generator and the transpose of that generator are equal. So we can prove then that this is the terminal operad, and that each part of it, which we refer to as the arity of the operad, is isomorphic to the ground ring. Now, the Comm operad is not great for homotopical purposes, so we're going to be thinking about how to resolve it. In fact, the notion of a resolution makes sense for any operad, and the correct notion in this context is a weak equivalence. Let's think a quasi-isomorphism of each arity induced by an operad morphism, and the condition that plays the role of injective or projective or free is the notion of sigma free, which tells us that the arity n part of the operad all is a free module over the group ring of the group sigma n. So in other words, we're demanding that the arity n part is a model for the universal bundle of the group sigma n. So if we have a resolution of the Comm operad, well, we're going to have multiple of those, and they're all known as E infinity operads. This is terminology that goes back to Peter May. Now, terminology that is due to Vortman and Vogt is the notion of an E infinity prop, and it's simply defined as a prop in which, when we restrict the number of inputs to 1, so we consider the associated operad, we have an E infinity operad as just defined. So this is the notion that we're going to be considering in this talk. Is this an E infinity prop? And what we're going to see is how to construct one such. Furthermore,
yep. One question. So there's no restriction on the operad having multiple inputs and one output?
Yeah, so we're in the operad context when we're defining sigma free resolutions.
No, so, I mean in the E infinity prop definition.
Yeah, so there's no restriction apart from the fact that when you forget structure to the one input and many outputs, you end up with an operad that is a model for E infinity.
So for example, if you look at many inputs and one output,
yeah,
that operad, that might not be contractible.
That's correct.
Okay.
Yeah, there's no extra conditions. We're only focusing on a part of the prop, although one could also ask what are the natural conditions that the other biarities satisfy, and we'll say a few words about that. So before I introduce the gadget that I want us to discuss today, I would like to make a remark, and that is that if we stay in the context of operads, it's impossible to give a finite presentation of an E infinity operad. Now, the gadget that I want to discuss with you is this prop that is given through the following presentation. We're going to have two generators, like in the Comm case, in the commutative operad, but we're also going to include this 2-to-1 guy that breaks the operadness of the situation. We're going to demand the co-unitality that we also had in the Comm context, and the interaction between the augmentation and the new generator, which I'm going to refer to as the product. This is going to be the co-unit, the co-product, and the product. So the interaction between the co-unit and the product is trivial. So they are 0. Now, we are lifting from the category of abelian groups to the category of chain complexes. So I also need to tell you in what degrees these generators are and what their boundaries are in the chain complex that is generated by them. So the degrees of the first two are 0, co-unit and co-product, and the degree of the product is 1. Now, the boundary of, again, the first two generators is 0, whereas the boundary of the product, this new guy, is given here. So notice that we have 2 inputs and 1 output. So what this is saying is, well, you're going to take a linear combination of applying the co-unit to the first input and letting the second input go through, versus letting the first input go through and apply the co-unit to the second input. And the theorem is that this prop is E infinity. So now I would like to say, how do we prove something like this, which will also give us more information of what's the structure in other biarities, not just the 1, n part, but also the m, n part of things. So here's the proof in quotes. So what I'm going to explain is how to compare the biarity mn and the biarity m plus 1, n. So what happens when we increase the number of inputs. So the claim is that these two are chain homotopy equivalent. And in order to prove that, I'm going to describe a pair of maps. We're going to convince ourselves that one composition is the identity. And I'm going to introduce a chain homotopy between the identity and the other composition. So it's very diagrammatical, and I hope we can describe these maps pictorially. So going from m to m plus 1 inputs, what we do is add this red line. So we apply the coproduct early on and just pass it through all the way to make it an output and re-index appropriately. So yeah, and now going in the other direction, what we can do is to kill one of the outputs here by applying the co-unit to it. So we lost one of the guys down here. Now, if we do the composition this way, go to the right and then come to the left, we see that the co-unit is being applied to this added strand, and that disappears thanks to the co-unital relation. That's composition equal to the identity. If we go in the other direction, we will use this this chain homotopy to make that composition the chain homotopic to the identity. So what we do is to apply the coproduct to get the strand, and then we use the product to bring it into the last output. So if we do this, we're going to be able to reduce the computation of the homotopy, or the homology, if you want, of this complex to be the same as that of this complex with 0 inputs, which I realize I am saying it reversed, and I'm sorry. So you have 0 outputs over here. So you have a 0 here, that means that the 0 is down here. I'm sorry for flipping things on you, but let's stick with the pictures. So we kill all the outputs and we end up having just this term, and the claim is at the very bottom we have a one-dimensional complex, because this is the only generator that can exist there, and therefore we prove the contractibility of these spaces. All right, so now that we have, in quotes, hinted to what the proof is about, I would like to move into another result that tells us what we can use this prop for. So I would like to focus on the chains on singular chains, or on the normalized chains on simplicial sets with more generality. And the first statement is that we do have a representation of the entire prop, that is by algebra, on the chains on the infinite simplex. And how do we describe that? Well, this is one of the advantages of having a very small presentation, because we can describe the bialgebras by simply identifying what the images of the generators will be. Then we have to obviously check that the relations are satisfied. So we're gonna send the co-product to the Alexander-Whitney diagonal. We're gonna send the co-unit to the augmentation. This is the map that sends, there's a linear map that defined on the basis by sending every simplex of dimension 0 to 1 and sending every other simplex to 0. And finally, the product is going to be the join. This is the novel element of this conversation. This join is illustrated here. We have the two elements 0 and 1 and 2, 3. We take the join of those two simplices to get the entire 3 simplex 0, 1, 2, 3. So we can also notice here that the degree of this operation is 1, which matches the degree that the generator had in the presentation. Now, once we prove that this bialgebra is there for the fundamental example of a simplicial set, then we can use a Kan extension argument to define a natural E-infinity coalgebra structure on singular chains, or as I said, on the normalized chains of any simplicial set. So here's a word of caution. This extension procedure does not carry the entire bialgebra structure to the chains. It only carries the E-infinity coalgebra structure. So there's lack of co-completeness, so we cannot extend the entire bialgebra structure, but we can extend this E-infinity coalgebra structure. So this is something we can ask now as well. What can we use this description of the E-infinity structure on chains of spaces? Well, one of the first things that we can think of is Steenrod squares. So let's say we want to know how to represent Steenrod squares at the chain level. So in 47, Steenrod produced an extension of the Alexander-Whitney diagonal, which I'm going to note delta 0, that corresponds to the co-product in our set of generators. And that extension corrected the lack of co-commutativity of the Alexander-Whitney diagonal, and he presented formulae for those. So what I'm saying here is that we can identify the same formulae with the action through the Alexander-Whitney diagonal, the augmentation, and the join with the action associated with this elements in the prop that we're studying. In this case, it's the sub-operad in that prop. Now, the reason why Steenrod introduced this homotopical corrections was to find invariants in the mod 2 cohomology of spaces, and those are known as the Steenrod squares, and they are defined, the relationship that exists between those and the cup-high co-products given by this expression. We take the cohomology class represented by some co-cycle alpha, and we apply the tensor product of alpha with itself to the output of applying this cup-high co-product. Now, the construction of this SQK doesn't really care about the particular choice that Steenrod made. Any other choice of corrections for the lack of co-commutativity will do just fine as long as it's in the same homotopy class. But it's fairly surprising that, well, surprising at first, that what you get through representing this graphs, these elements in the operad, is the same formulae that Steenrod got. And in fact, every other time that those co-products have been chosen, the formulae are the same. So I would like to maybe pause here a little bit the main discussion of this problem and make a little sidebar about those operations. So the question of why they are so well defined in a way, or why they keep appearing, even though for steam-rod squares you can take any other one that is in the same homotopy class, is that these choices that steam-rod made and that they're reproduced by this prob are unique if one extra requirement is imposed, and that's a sense of freeness. So we want simplices not to reappear if we apply some transposition. The notion of freeness here requires more expansion if you really want to understand it. But a first good approximation is this idea of free with respect to transposition, and simplices should not reappear. So the way that I like to think about this theorem, and maybe the full explanation of it will require a different talk, but on passing, I will say that kind of the slogan that goes into this, at least in my head, is to think of harmonic representatives on homology classes. So there's a geometric reason, in our case, more of a combinatorial reason why there's a preferred representative on a given class. For the case of harmonic representatives, we minimize a certain energy, and over here, the class of finding choices of kappa i's, we are requiring this extra freeness. And the other quote-unquote theorem that I would like to mention, again on passing, because this could take a different talk, is that this particular choice that steam-rod introduced early on and that is being reproduced every time is precisely the data that one would need to define the nerve of strict infinity categories. So this is known as the street nerve, and the combinatorics that is encoded on the steam-rod kappa products agrees with the combinatorics that goes into the definition of the nerve, or more specifically of the free strict infinity category on the simplex.
Anibal.
Yeah.
Can you say a little bit more about that? I don't know what the nerve of a strict infinity category means.
Yeah, so that goes by the name of street nerve. So another word for strict infinity categories is omega categories. So this is the notion, the very strict notion of categories, n categories in reach over n-1 categories, right? So what you need to do in order to define the nerve, let's say in the category context, is to say how to equip the one simplex with the structure of a one category. And then you're going to consider all category morphisms from that free object and from that free object into a category. So that's the usual notion. And that can be assembled into a simplicial set. So what we're going to try to do here is to start with one of these strict infinity categories and produce a simplicial set. And in order to do that, we need to not just know how to make a 0 simplex and a 1 simplex into a category, but we need to be able to define how to make all the simplices into strict infinity categories. So then you're going to take morphisms in the category of omega categories, and that assembles into a simplicial set, which is called the nerve.
Have you thought about how this compares with the homotopy coherent nerve?
I haven't thought about that yet. Maybe it would be good if we take a moment afterwards to see connections there. Yeah. So, and what I'm saying is, you see, the key element in order to define this nerve is to be able to say, how do you make a simplex into a strict infinity category. And that's a combinatorial problem that Street solved in the 80s. And the claim of this quote-unquote theorem is that that combinatorics is actually the same combinatorics that goes into defining this preferred, this special, this quote-unquote harmonic choice for Steenrod-Kappa coproducts. But as I said, I'm not going to dwell into this. I just wanted to, on passing, make that connection. And before we go back to the study of the C infinity prop, which is where I'm focusing in this talk, I will also try to answer a question that hasn't been posed, but it could have been posed, which is, well, we know that at other primes, there's similar operations that exist. Those up to now have been only defined implicitly. Now we don't have formally defining the analog to the Kappa products for cases that are not the Steenrod squares, but they are the p power operations that Steenrod defined for the p cohomology, or the cohomology with p coefficients, fp coefficients, where p is a prime. So just again, on passing, before we go back to the main focus, I would like to say that we already solved that question. How do we, this is joint work with Ralph Kaufmann. We fill in this gap in the literature of what is the analog for the Kappa products when we try to represent power P operations. And as an example of the type of combinatorics that we'll find, an object representing this operation, the analog to the Kappa product, would be given by this linear combination of elements. Anyway, so if there are no more questions, I'm going to go back to the study of this A infinity prop. So when we were discussing the representation of this prop on the infinite simplex, we say that the Alexander-Whitney diagonal and the join were the images of two of the generators. But we observed that those two maps satisfy more relations than those that are satisfied, that are imposed on the prop. Namely, the Alexander-Whitney diagonal is co-associative, the join is associative. There's a sort of Leibniz relation between the two. There's an involutive property between the two, and the join is commutative. So if we're to take the hint seriously and say, well, what do we get if we take those as part of the finite relations that we have? Well, we're going to define a new prop, turns out to be also an E infinity prop. I'm going to refer to it as the MS. In order to identify what this guy is, let me tell you about a map that we have here. So it would be maybe easier if I go back a little bit. Excuse me. Maybe this is enough. We can think of this picture here, this graph. We could have represented it much more succinctly by just remembering where it lands, where each of these strands land. I have 5 of them, and they're equipped with an order. So I can talk about the 1 strand, the 2nd, the 3rd, the 4th, and the 5th strand. And here in the outputs, we also have a total order. So we have the 1, 2, and 3. So I can just represent the image. If this was a function, 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 1, and 5 goes to 2. So I could represent each of these guys just as a sequence of numbers, and in fact, as a surjection. And this is the map that we have here. So if we have an element like this, several strands at the top, so we're going to have surjection that will take us, well, we'll demand it to be a surjection, but we'll have a surjection that goes from n plus something, the number of strands at the top, and going to 1 to n, the number of outputs that we have here. So the claim now is that if this requires that you might have encountered this operand before, but there's a nice model that is very small. It's not finitely presented, but it still is one of the smallest models for E infinity that we know of, and that is due to McClure-Smith. Berger-Fresse also used it. And the claim is, if we take this MS and its associated operad, then this assignment that we discussed between the graphical representation and the surjections induces an isomorphism of operads. So if we put these extra conditions that are satisfied in the representation for simplicial sets, then the model that was finitely presented, we take the operad, reduces to one that we already know and we like. Now, one of the things that the surjection operad cannot do is to act on cubical chains. And one of the advantages of not passing to the quotient by all those extra relations is the fact that there is an S bialgebra structure on the interval, which is the one simplex, so we already knew it from before. And that S bialgebra structure extends via the monoidal structure to all cubes. And when we extend to all cubes, again, through a Kan extension, we can define natural E infinity coalgebra structures on cubical chains for any cubical set. So again, this is a good point to maybe pause, and we're going to continue now. Now, I would like to move now away from the algebraic category and think in terms of CW complexes. So we said that the product was a degree 1 generator in the algebraic context. Actually, we can think of it as an interval. This the value S runs between 0 and 1, and the attaching map to this one cell is depicted here. So in one extreme, we attach to this picture, and this other extreme, we attach to this picture, which, if we were to go back to the algebraic context, will give us the boundary that this generator had. Now, one of the reasons why one can say that maybe this prob has better properties with respect to cubical things is that each of these elements it's itself homeomorphic to a cube. So the dimension of the cube is the number of occurrences of the product inside of it. And the attaching map of that cube into the SMN space is again given by cutting off one of the strands when it goes to 0, and replacing that, cutting it off and cupping it with the co-unit. So in the CW context, we can also try to understand better what this prob looks like. Maybe if there are connections with earlier work, and that's what we're going to do now. There are two elements that will go into the recognition of this prob elsewhere. The first one is to change coordinates in a way. So far, as you can see, we are providing weights to the vertices, certain vertices in there. We're gonna change coordinates to provide weights to all edges. And the second step will be to recognize further structure in the underlying graph. That is the structure of a Riemann graph. So let's start with the change of coordinates. So we're going to go from weighted vertices, as I said, to.
Can I ask a question? Sorry.
Of course.
Yeah. I'm not sure I understand here the picture. So the dimension of the cube corresponds to the number of product applications. Is
That's
that
right?
right?
That is
Okay.
correct.
And is there a compatibility between the boundary of the cube and the boundary of the properad?
Of the prop?
Yeah, of the prop, sorry.
Yeah, yes, indeed.
So so when you said when any of these parameters go to 0, what's happening here with the operation? I'm not sure.
Yeah, great. So how about we take a look at the top part, which is a very simple case of what's on the bottom. So over here, the entire element in the prop is just the so-called product, right? And it is equipped with a parameter, a real value between 0 and 1. So I can think of that as an edge. And now I would like to attach that edge into the cellular space S to 1, right? So I'm going to attach this cell by putting its 0 endpoint and attach it to this element in that cellular space. And this is a 0 cell in the space, and attaching the other end to this 0 cell over here. Okay. So I'm thinking of building the entire the entire SMN CW by attaching cells. And the observation is that those cells are all homeomorphic to cubes, and the attaching map is understood in terms of cupping off or cutting off edges that are incident or they're coming into a product.
I see. Okay, I see.
So yeah, if you remember that there are no more. Yeah, go ahead.
Yeah, you cut off that edge, and then you have to record a number, right? Which is the co-unit applied to that incoming edge, right?
If I mean, if you're thinking algebraically again,
right, we're in
you want to represent it, that's exactly what you would be doing.
Yeah, but we're in the CW case. Okay, good.
We're in the CW case, and I'm not talking about any representations, any bialgebra. There are no bialgebras now. We are in the more abstract context of just understanding the prop before representations. I see.
Yeah.
And maybe this is a good point. Actually, I would like to. I didn't put this in the slides because I thought I wouldn't have time. Since it already arose, one could ask, well, where does this CW version act? And one of the natural things is it actually acts on the geometric realization of simplicial sets. Those are CW spaces, and in fact, the action is in the category of CW. So in the same manner that we saw how there's a bialgebra structure on the infinite simplex when we take the chains on it, if we were to take the geometric realization and not the algebraic realization, this prop will act on it, providing it with the structure of a infinity bialgebra. And again, by Kan extension argument, we will have an action of this cellular prop on the geometric of the associated cellular operad on the cells on the geometric realization of simplicial sets.
And similar for cubes, right? For cubical.
Well, that's a red herring, actually. Yeah, I'm gonna have. There's some technicalities there. I know you've thought a lot about cubical sets, so maybe we can talk about some of the issues that go into making the exact same statement.
Yeah,
there's one that is.
Yeah. Okay. Good.
But it is true that in the algebraic context, there's no red herrings to actually get the action on cubical chains. In the CW case, there's some some little issues. Anyway, so let me again recap what I'm going to do. I'm going to try to recognize the CW context in earlier contexts. And there are two elements, the Riemann structure that I'm going to introduce next, and what this slice does, which is tells us how to change variables from weighted vertices to weighted edges. So the first thing is to go at the very bottom and make all of those to have weight 1. So that's free. We just put those edges to have weight 1. And the other step is to look for this co-units, and all of those have weight 0. So the edges that end on this co-unit have weight 0. And the edges that go all the way out, those have weight 1. But now I need to tell you how to propagate, in this case, upwards. So if we know x here, which is the weight before the vertex, and this is the vertex associated to a product, well, that vertex is equipped with an integer, with a real between 0 and 1. Now we're gonna make the weights of the other two vertices, the unweighted ones, to be the product of s with x and 1 minus s times x. So we're propagating upwards the weights that we started by defining in the output to be all equal to 1, and we'll continue. Every time that we encounter a product, we apply this rule, and every time we encounter a co-product, so we know the weights in the bottom, x and y, then the missing weight is just the sum of the two. So just change of variables, nothing new. It's just because we're going to use it later on. Now, the other element is the Riemann structure. So at the very beginning, we saw that there's an implicit total order on the outputs here, those two guys, the total order here. There's a natural way of providing every vertex with a cyclic order on its incident edges. And that's what's called a Riemann structure. And there is a procedure, which I'm going to call surfaceification. I actually had to practice saying that word, that will go as follows. So we start with the ribbon graph here. In our case, we're also going to put a little circle. We're going to attach an interval to the endpoints. So we start by doing that first. And well, that's still a ribbon graph. And now we do the construction of the associated surface. We just go around marking it in one direction. And every time we reach a vertex, we know what the next edge is. So we continue marking that edge. And the Riemann structure tells us that every time that we go an edge, we know how to continue. It may happen, like in this case, that if you follow this procedure, you come back to where you started. So you have this green path. And then you just start again until every edge has been passed through twice. Again, the Riemann structure tells you that it's what's going to happen. And now that you have this paths, this red and green ones, you go ahead and attach cells following those. And the output is a surface. In our case, it's going to be a surface with boundary components, with punctures. With boundary components. And since we have a directedness, we can say about the input circles and the output circles. So that is the second element that we're going to consider. So if we put them together, if we start with one of the elements in this CW prop, we end up having a surface with boundaries in incoming circles and outgoing circles, together with one skeleton that is weighted. So again, to make the connection to, and I should say, this will be a model for E infinity because I haven't done anything. I can just push forward the composition structures. So But to make connection with earlier work, I'm going to again mod out by certain relations, co-associative, associative, involution, and Leibniz again, and to the result cellular prop, I'm going to call it MS with the CW on top, and I noticed that I forgot to put the CW here in S. And now we have a very similar theorem to the one that we saw in the algebraic context. In this case, if K E infinity denotes Ralph's arc surface model of the E infinity operad, then this surfaceification procedure restricted to the operad associated to this cellular prop gives you an isomorphism of operads. And one nice corollary of it is that it creates this connection between the chains on Ralph's model and the surjection operad, because if you were to take the chains on this MS model, what you would get is what I was calling before the MS without any superscript, so the algebraic model. So we have this corollary here, which actually Ralph already conjectured, and now we have this little proof here. So I want to end with some future work. There's this slogan that I'm trying to explore, which is that this prop S is to cubical, like the Berger-Fresse, another well-known model for E infinity, is to simplicial. And one of the manifestations of this would be to say the following, that the coalgebras over the operad associated to S admit a natural model category structure. This is true for the Berger-Fresse operad, and the reason why it holds is because it's equipped with a nice diagonal. And that is a consequence of the fact that the Berger-Fresse is itself simplicial. So now we have this model that is more cubical, acts on cubical chains, and it is equipped with a diagonal as well. So that's the basis for that conjecture. And with that said, I thank you for your attention.
So let's thank Anibal. Thank you, thank you. So are there any questions?
I have a question. So you said that like E infinity is not finitely presented as an operad?
Yeah.
And I guess I apologize if I missed this, but are there any like Andre Quillen, homology groups that don't vanish that like demonstrate that or something?
The argument is just with Steenrod squares.
Yeah, but I guess, is there another way? Can you?
Is there another way?
Yeah, or I'm just saying, like, shouldn't there be a group that measures? Like if you think like, what are the generators of a operad? Or how do you measure generators of an operad? Shouldn't that be like operad indecomposables, which is Andre Quillen, underived Andre Quillen homology or something? And then is there some group that would like, whose non-vanishing would measure the like, I don't know, whatever, we can, maybe I'll send you an email later or something.
Yeah, I hear you, and it's very intriguing. Actually, I haven't thought about it. Yeah, so I'm looking forward to that email.
Okay, yeah. Yeah, I would talk to you afterward, but I have to go. But yeah, I'll send you an email. And maybe
Awesome.
We can talk later.
Any other questions or comments? So I know we discussed some subtleties regarding cubical sets and so on, but I forgot. Can we recall that quickly?
Yeah, so let's see. So one of the things that one would like is to go, let me see where we are. Let me find that. I guess this is the best place to be. So when we were talking about the CW thing, I make the claim that is easier to prove that the geometric realization of simplicial sets naturally carry coalgebra structure over the associated operad to this cellular prop. And I also make the claim that it is a cellular, all the maps that go into defining that structure are cellular.
So just, just a comment here. So let me try to think about this. So, I mean, any topological space, let's not necessarily CW complex, it's a kind of like a coalgebra, stupidly, right? I mean, not stupidly, but just by the diagonal map.
Yeah.
So this is kind of making this into a cellular statement or something.
Yeah. So staying over there, if you imagine what that, let's call it natural coalgebra structure in a space would be, if you restrict to the interval, then you want to map that interval into the square, and that will be mapped to the actual diagonal.
Right.
So that map is not cellular because it's going to higher cells, a two-dimensional cell. So then, in the same way that this is very similar to what you would do in the algebraic context, you want to have a chain approximation to the diagonal. Here, we want to find a cellular approximation to that same diagonal that you're thinking about. The issue is, well, if you take an approximation, the resulting coproduct is no longer co-commutative. And that brings back this whole E infinity structure, which can be described neatly in terms of just three operations.
And now for cubes, what's the issue, sorry?
For cubes, the
for cubical sets, I mean.
Yeah. So I haven't discarded it, but there was the resulting map, the natural extension of what, and yeah, maybe I should say this. If you have my goal was to say, oh, I only need to define this bialgebra structure on the interval. And then use the monoidal structure that generates the cubes to simply extend that bialgebra structure on the interval to all cubes, and then a Kan extension will give us the coalgebra on geometric realization of cubical sets. So what I failed to do before this talk was to being able to extend the natural bialgebra structure on the interval to the rest of the cubes. And there was an issue with the map that resulted were not cellular. So I'm not saying that it's impossible, like the other claims that I made. It's just that I haven't ironed that result yet.
Okay, and why is this not a problem on the algebraic context where you're looking at chains on cubical sets?
So I think at that point there's this you can map things to zero. That's probably the most abstract and higher level reason. Yeah, but again, it's not necessarily failing. It's just that I didn't iron the details yet, or I haven't found a real reason for it not to hold.
Okay, that's good. Thank you so much.
Yeah.
Any other questions or comments? Okay, so let's thank Anibal again.
Thank you very much.
Let me